Today we're going to talk about integration in polar, cylindrical, and spherical coordinates. So in order to talk about that, our first learning goal is we're going to have to define cylindrical and spherical coordinates, something that you may or may not have seen previously. Then we're going to set up integration in cylindrical coordinates, and we're also going to end up setting up integration in spherical coordinates. Given certain types of regions, these coordinate systems will be more computationally direct. Usually at this point in the videos I don't introduce any formulas, but I have some formulas that are important enough that I'm going to go ahead and introduce. That when dealing with cylindrical coordinates, we're dealing with functions of r, thetas, and z's typically. We need to add in an r, dr, d theta, dz. And this is something that I'm highlighting, that we have this term of integration of r. And when we do spherical coordinates, similarly, we're doing a triple integral, although in this case usually our variables are phi, or rho, phi, and theta. And we're going to add another term of integration, although this is a more complicated term of integration. It's going to be rho squared sine of phi, d rho, d phi, d theta. Again, these can be in any order that we want. But these terms of integration are something important that I want you to record because they'll be needed. So our first definition is going to be the definition for cylindrical coordinates. We define our cylindrical coordinates as a coordinate transformation for which x is equal to r cosine theta, y is equal to r sine theta, and z is equal to z. Notice that this isn't anything that should be that new to you, because this is exactly how we define polar coordinates. So visually in this space, if I now look at my three-dimensional space, instead of having an x-axis, a y-axis, and a z-axis, I'm going to keep the heights or the z values the same. But instead, visually when I measure this out, a point in space, here I'll put a point down here on what would have been the xy plane. Maybe I'll write it in blue because now we'll be talking about polar coordinates. Theta is going to be the angle that we make with the positive x-axis. R is the length out away from the x-axis. And z is the height of the point vertically. So if I pick some point out here in space, I could describe it in terms of what angle. I'm going to project it down onto the xy plane, and I can describe this point in space as the angle that it's making with the positive x-axis, the length out it's making from the origin along the x-axis, and then the height of that point. And that's what I mean by cylindrical coordinates. So let's see an example of cylindrical coordinates. For example, let's say I want to describe a cylinder. That's why it's called cylindrical coordinates, because cylinders are easy to describe, of radius 3, where the circular part, maybe I should say that this particular cylinder is given by the formula x squared plus y squared equals 3 squared. So if I were to visually draw what this cylinder looks like in the xyz plane, we would have a circle in the xy plane. Our z values are unrestricted, so they can go up as high and as low as we want. And our radius in this case is 3. So if I wanted to convert this cylinder and to describe it using polar coordinates, there are two ways that I could think about doing it. I could visually evaluate it, or I could algebraically evaluate it, and I'll show you both methods. My first method is algebraically. I could say, aha, I know what x squared is. X is given by this. So when I convert it to polar coordinates, it becomes r cosine of theta squared plus r sine of theta squared, because my y coordinate is r sine of theta, has to be equal to 3 squared, which is 9. I can distribute this squared, and I get r squared cosine squared theta plus r squared sine squared theta is equal to 9, I can factor out my r squared, and I get r squared cosine squared theta plus sine squared theta, and we know that cosine squared theta plus sine squared theta is just equal to 1. So my equation, r squared equals 9, or r equals 3. Notice I'm not actually going to do plus or minus 3 in this case, and the reason why is that a minus 3 radius doesn't make sense. Typically we restrict ourselves to thinking about positive radii when we're dealing with cylindrical coordinates. That's a convention that isn't a universal convention, but it's something that we're going to do. We're going to restrict our r values to being positive, because if I wanted to think of a negative r value, I could just change my theta angle. So final conclusion, a cylinder of radius 3 in my cylindrical coordinates is given by r equals 3. That doesn't look like much of an equation, right? Well, the reason why it's not much of an equation is because embedded in this idea, if r is equal to 3 and I don't have any of the other variables listed, that means I'm thinking to myself that my z is unrestricted, meaning that my z values can be as big and as small as I want, and I also know that my theta is unrestricted, meaning that this cylinder is tracing out a full circle, or as many circles as I want. Typically, again, we restrict theta just being positive values between 0 and 2 pi. So I'm going in a full circle and in as many heights as I want, but my radius is kept constantly at 3. The second way to evaluate this is to visually evaluate it. So I could think of, what does any point somewhere on this cylinder look like? Well, I know the points on this cylinder are all going to be a distance 3 away from the origin. I also know that points on this cylinder can be as high as and as low as we want. And I also know that the points on this cylinder can be anywhere from 0 to 2 pi. So just by visually evaluating what this cylinder looks like, I can also come to the conclusion that r equals 3. And I might even say that 0 is less than theta is less than or equal to 2 pi, meaning I could go in a full circle in terms of my theta, and my z's are as high and as low as I want. The z's are unrestricted. So if I just wanted to do a visual analysis, that's going to exactly align with the algebraic computations that we did previously. So next I want to introduce spherical coordinates. A spherical coordinate system, as the name suggests, makes it really easy to come up with equations for spheres. There are 3 different coordinates that we use for spherical coordinates. Instead of using a z-coordinate, we're going to use these crazy coordinates. The first one is rho. This is the Greek letter rho. R-H-O. It's sort of analogous to our radius that we had in polar coordinates. That rho is the distance from a point to the origin. And then theta, our next coordinate, theta is going to be exactly the same thing that it was in polar coordinates. It's the angle that you make with the positive x-axis in the xy plane. So our theta angle, again, can go from 0 to 2 pi. Our final coordinate is phi, another Greek letter. Some people call it phi. I'm going to call it phi. It goes from 0 to pi, and it's the angle that's made with the z-axis. So visually, what is going on here? I dropped my eraser. Sorry. So visually, we're in a 3-dimensional space. So this is how I'm representing my 3-dimensional space. And I have some point in this 3-dimensional space. This point, the easiest one to find is rho. Rho is just the distance from that point to the origin. So it's exactly like our radius. It's the length that this line traces out. I'll label that one as rho. But the other 2 are a little harder. This theta angle is the angle that's made with the positive x-axis. So in order to be able to compute this, we're going to have to project this point down into the xy plane. So I just projected this down at a 90-degree angle. And I want to know, what is the angle that's traced out from the x-axis? That's exactly what our theta is. X, y, z. So if I were to take a bird's eye view, it would be exactly what theta is in polar coordinates. It's the angle that it's making with the x-axis. So notice that this gives us some information, but it doesn't give us all the information. We have the distance from the origin. We have how far we're swinging out away from the x-axis. We also need to know how far we're dropping down from the z-axis. And that angle is measured by our angle phi. A word of caution is that the names for these angles is not standard. If you look up other textbooks, particularly physics textbooks, or other applets that are available online, they might switch the names of phi and theta. So just beware of that when you're looking at other sites online. And I actually will probably give you some links to some applets that look at those. So in general, this is how we're describing points in space. Instead of moving in an x direction, a y direction, and a z direction, we're going to say how far out from the origin are we traveling, what angle are we making with the x-axis, and what angle are we making with the z-axis. For your benefit, maybe my benefit as well, we can describe these coordinates. If I have a coordinate and it's labeled as the point x, y, z, how am I going to be able to convert it into these thetas, phis, and rhos? And the answer is we're going to have to use triangle geometry in order to be able to convert these. So the easiest triangle to figure out is the fact that if my height is up here at z, what is z? Z in this case, I can look at this triangle that's formed right here. Maybe I should do these all in different colors. So when I'm doing my z, I'm going to look at this triangle right here. And I see that the hypotenuse of this triangle is given by my rho. And I see that this height, z, this is z, and is going to be the adjacent side to this angle phi. Meaning that if I were thinking of this as a triangle, the cosine of this angle phi is going to be adjacent over hypotenuse. And I'm going to write that down. We see that the cosine of my angle phi is going to be this adjacent side, z, divided by the hypotenuse, which is rho. And if I solve for z, it means that z is exactly equal to rho times the cosine of phi. This side length here is the cosine, or this side length is equal to this length rho times the cosine of phi. The other sides are a little difficult. So that was my z side. Let's say that I want to take a look at what is my y coordinate. My y coordinate in this case, I need to know two things. Two things are going on here. I'm looking sort of down in this plane, right? So we already found this triangle, and we know that this height was rho cosine phi. Rho cosine phi. This length right here is rho sine of phi. It's opposite over hypotenuse. So this length ends up being rho sine of phi. This length right here, maybe I didn't draw this picture super well, is exactly this red length down here. So the red length is also rho sine of phi, right? Because this is my phi, this is how much it's going out. I'll angle this a little better because this is a point somewhere out in 3 space. They should have the same angle, right? Where this is actually the right angle. Regardless, down in this xy plane, I now know that this radius here is rho sine of phi. And I want to know how far over am I going in the y direction. I'm going to have to look at a different triangle. I'm going to look at this red triangle. Maybe I'll label this hypotenuse rho sine phi. I have this angle theta. If I were to do a bird's eye view, this is my bird's eye view. I'll try to keep this consistent. So this is my x coordinate, and this is my y coordinate. Rather than thinking of my xy plane this way, I've tilted it this way. So in this picture, I have theta as my angle here. And I'm going to make a right triangle where the length of the hypotenuse is rho sine phi. And it means that this length in the x direction, if this is my angle theta, theta is going to be my length of x. It's adjacent over hypotenuse, so that means that the cosine of theta is going to be equal to the adjacent side, which is x, over the hypotenuse side, which is rho sine phi, which means that x in this case is given by rho sine phi times cosine of theta is equal to x. And similarly, when I want to know my y-coordinate, my y-length is down here, so my y is given by the sine of phi, and it means that my y-coordinate is going to be rho sine phi times the sine of theta. And that's all just using triangle geometry. You don't want to memorize all that. This is a way that you could recreate it. Or you could just write it down and memorize it. So let's go ahead and see an